So we begin today's session with Professor Gian Giudice, who's going to continue on his series of talks. So today he's going to talk about self-organized localization. And over to you, Gian.
Fine. Okay, so thank you very much. Can you hear me okay? So today I want to give a concrete example of what I was discussing yesterday in the multiverse, so the goal is to show you our ideas, but also to show you that what I was discussing yesterday is not only words, but it can be put in a very concrete way. And indeed, I should warn you that so today is going to be a rather technical talk. And I'm going to go into more of the details. But so it will show that it's not, these theories are not simply words, but really you can put them in equation and get very concrete results. And as you see, also experimental results. It can also lead to experimental consequences. I mean, it's in general, it's hard to say what are the experimental consequence of the multiverse, but in a sense, it's a question like what are the experimental consequences of quantum field theory? I mean, you can't answer, right? You have to say what are the experimental consequences of the standard models. You have to specify the theory. In a sense, you'll see also the consequences I will talk about today are very much related to the specific example that I'm considering. But nevertheless are very well defined, and this is based on work that I've done at CERN together with Matthew McCulloch and Tae-Wong Yu. So the critical phenomena have always played a central role in physics since the time of Ehrenfest and Landau. And also phase transitions are known to play a fundamental role in the history of the universe. Take the QCD or the electroweak phase transitions, and then phase transitions may be the cause behind phenomena like inflation or baryogenesis. But these are classical phase transitions. So in a classical phase transition, the phase of the theory changes as the temperature is varied. Take the case of the ferromagnet. When you lower the temperature below the Curie temperature, then order spontaneously emerges in the form of a bulk magnetization. So classical phase transitions are familiar ingredients of cosmology. But here I want to consider quantum phase transitions. So in a quantum phase transition, it's not the temperature that varies, but some external field, for instance, the magnetic field. Let me make a specific example. So take a microscopic theory in which you have an operator O coupled to an external field phi. The value of O is 0. Below a critical value phi c, the theory makes then a phase transition and O develops a valve. As a result of the sudden phase transition, the first derivative of the potential V of phi has a discontinuity at the critical point. In other words, the first order phase transition of the microscopic theory makes the phi potential non-trivial at the critical point. So my goal is to use quantum phase transitions as trigger to determine physical parameters. And the idea is based essentially on two ingredients. The first is that some parameters of the microscopic theory, and by microscopic theory, I mean the standard model or any of its BSM extensions, and are promoted to functions of one or more scalar fields. So during inflation, this scalar field is light with respect to the Hubble rate, and therefore its background value varies stochastically as a result of quantum phase transitions in the Sitter space. As the scalar field random walks in its field domain, the standard model parameters change in different parts of the universe and at different instants of the cosmological history. So effectively, this means that there is a multiverse where the standard model parameter take all possible values in different space-time patches of the universe. This is similar to ideas that I've mentioned yesterday, right? In particular, the case of the axion. The second ingredient concerns the selection mechanism. In other words, how a particular value of the standard model is selected out of all possible values that can be realized in the multiverse. So yesterday I mentioned some of the possible selection criteria, right? One I just mentioned, didn't have the time, was that theta QCD is selected by a symmetry criterion in the case of the axion, because the scalar potential is minimized at the point in which CP is conserved. And I also discussed the case of Weinberg proposed an anthropic selection as a way of selecting the cosmological constant. I didn't have the time, but I imagine that you are familiar with the relaxion, which uses a back reaction from electroweak breaking. And what I want to propose today is that criticality is the selection mechanism. So criticality and not symmetry may be the secret for understanding the values of some of the parameters of a low energy theory. So that the universe dynamically prefers to be at the verge of a phase transition, in a metastable state, ready to collapse to a different phase. So the low energy parameters are dynamically selected to place the universe at a critical point, even if these values do not correspond to a point of enhanced symmetry. So let's see now how self-organized localization, which is the name that we gave to this mechanism, so I will say SOL in short, and see how it operates. So the language that I've chosen to use is the one of the stochastic approach introduced by Vilenkin, Starobinsky, Linde, and many others. So the central variable is a distribution P of phi and T that describes the volume occupied by the field with a value phi at the time T in an expanding universe with Hubble rate H. And this is the equation. That the dynamical equation is what is called the volume weighted Fokker-Planck equation, which I will call it FPV. So the time evolution of P is determined by three terms. So this is the classical terms that describe the tendency of a field to reduce its potential energy as a result of the classical force, which is proportional to V prime. V is a scalar potential, and the prime denotes the derivative with respect to the field. And this term describes the quantum effect. So in the language of statistical mechanics, it is the diffusion term that broadens the distribution as a result of thermal fluctuations. But in my language, it's a pure quantum effect. And the third term describes the expansion of the physical 3D volume in the Sitter space. So it is interesting that the dimensional analysis shows that these three terms correspond respectively to classical physics because it persists in the limit h bar to 0 and m Planck to infinity. The second term to quantum physics because it vanishes in the limit h bar goes to 0, it's proportional to h bar. And then the third term is gravitational because it vanishes in the limit m Planck to infinity because it goes like 1 over m Planck squared. So SOL is really an effect of the three pillars of physics: classical mechanics, quantum mechanics, and general relativity coming together in the description of critical phenomena. So the physical meaning of the FPV can be traced back to the known result that the Fokker-Planck equation gives the average over a large number of random walks described by the Langevin equation. So I remind you that the solution to the Langevin equation gives a single trajectory of the field subjected to the classical force proportional to V prime and to a Gaussian random noise proportional to the Hubble rate. So this is what describes the quantum effects that randomizes the trajectory. The additional volume term in the FPV means that when taking the average, we weigh each of the trajectory, each of the Langevin trajectory with a volume factor e to the 3ht, which describes the expansion of the physical 3D volume space, right? Because of this additional factor, P loses the meaning of a probability distribution. The solution of the usual Fokker-Planck equation, the one without the volume term, is a probability because it describes the probability distribution of the Langevin trajectory, and indeed it has a conserved current because the time variation is equal to a total field derivative. In the FPV, this is no longer true because the weighing factor with the volume spoils current conservation. Therefore, the solution of the FPV is not a probability, but a volume distribution whose normalization doesn't remain constant with time because the total volume keeps on expanding. So I will use the asymptotic steady state distribution P, it is the solution of the FPV equation at large times as my thermometer, as my measuring tool to make probabilistic prediction in the multiverse. Now, this, I should warn you, is a controversial statement if you can make a probabilistic interpretation of that. So before I continue, let me open a parenthesis and discuss all the various open issues related to my probabilistic interpretation of P. So the first one is the gauge dependence of my parameterization, or in other words, the dependence on the choice of time foliation. So to test this gauge dependence of my result, I redefine the time coordinate according to this law, where h is the field dependent Hubble rate and h naught is a reference value. And you can choose it freely, and I choose it as a characteristic or the average value of the expansion rate. And psi is a number that varies between 0 and 1, which parameterizes the gauge. Obviously, this is not the most general coordinate reparameterization, but it describes a family of gauges as I vary psi. It is a representative family because as I vary the parameter psi from between 0 and 1, I interpolate between two interesting cases. When I take psi equal to 1, I get what is called proper time. And when I take psi equal to 0, I get what is known as the E-folding gauge, which corresponds to a time coordinate which measures the number of E-foldings accrued by each path. So in this special gauge, the volume term becomes exactly field independent. Therefore, it simply amounts to an overall time-dependent rescaling of the solution. But the field value has no impact on the volume weighing procedure. Since for us, the field dependence of the distribution P is central for the selection criterion in the multiverse, this case, the most pessimistic choice. So what I find is that the localization of P at the critical point is a gauge independent result. However, the degree of the localization, which is measured by the width of the distribution P, is gauge dependent. Okay, with the distribution getting broader, xi goes to 0 because that is a e-folding gauge. In all practical application, the distribution is parametrically so sharply peaked that the localization is lost really only if you put xi equal to 0 with an astronomical accuracy. Of course, this is not satisfactory. It's not satisfactory that the result have a remaining gauge dependence, even if it has little impact on the result. But so in that sense, I should tell you that my result should be regarded as an indication for an underlying physical phenomenon. A second different but not completely unrelated open issue is a well-known measure problem. So to make a probabilistic interpretation, you have to define the statistical ensemble in the multiverse to compare probabilities for the outcome of any single universe. So a meaningful way to do it is to compare universes at the corresponding reheating times. This is because the reheating is a moment at which observable universes are born. So since we are interested in the probabilistic distribution of standard model parameters at the time inflation ends, we must compute the distribution of the field phi on the reheating surface. So the reheating surface, I remind you, is a 3-volume hypersurface of all the reheating events in space-time. However, the reheating surface can be computed only once the inflationary model is specified, and we don't know what is the right model of inflation. Moreover, a big, yes, please. No, it is the usual gauging. That is the usual coordinate diffeomorphism of the coordinate reparametrization. So it is there, okay, in your theory. Now, with this choice in some separating space and time, I'm using a foliation. The remaining gauge dependence is just on the definition of time. TC. So time doesn't have no. The time is just a parameterization of the coordinate. So there's no field dependence there. Okay. It is that every time you have to reinterpret time. I mean, it has a field dependence in the sense that it's much more complicated than in a uniform universe, because in this case you have patches that expand in a different way. So this is the problematic of foliating your space. When you have an uniform evolution, say take a usual case of inflation, then it is clear that the field phi is the inflaton plays the role of your clock. So then it's clear how to separate time and how to define. There is a preferred way of defining time. Of course, there are odd ways of doing it, but it is. In this case, instead, since everything is non-uniform, there's not one single way of defining time, and that is the problematic thing. And when you define probabilities, however, you have to compare a universe here with a universe there, and therefore you have to make a choice of time. My point is that since I will use this, and you'll see it later, this steady state solution, when you go to very large times, at a certain point, you reach a kind of thermal equilibrium. And then at that point, the choice of time doesn't really matter, okay? But as I told you, when you're looking at the spread of the distribution, there is a remaining dependence on this gauge choice, okay? Thank you for the question. So back on the measure problem, and I told you that there is a difficulty of defining the reheating surface in this case. However, an even bigger problem is when you consider eternal inflation. And as I will show you in the following, all the applications that I consider requires eternal inflation. So in eternal inflation, new universes are continuously created, and the reheating surface is infinite and non-compact. So the nature of the reheating surface in eternal inflation makes any probabilistic interpretation difficult, not only in practice, because we don't know the model of inflation, but also in principle, because any relative probability is infinity divided by infinity. And this is the measure problem. There are several ways that have been proposed in the literature to deal with this problem and to regularize these various infinities with different procedures, but it's fair to say that that none of them can be regarded as the final answer. Please. No, well, but this is, I will get to that. This is indeed an open problem, okay? That with this parameterization, in principle, you end up with the Youngness paradox or the Boltzmann-Brain problem. However, it's very easy to show that you can modify your definition of the measure and avoid those problems. Now, is that a solution? I'm not sure. It looks like a little bit like a trick because I don't know what is the measure, okay? Certainly some of the measures will run into difficulties with the Youngness paradox. Well, Stochastic is a bad one. No, you can make it easily work if you just make the story slightly more complicated, and then you unrelated then the parameterization of time with the distribution of universes. So, but this is in a sense that this is for me is just the problem resurfacing. The underlying problem is that I don't know how to define a probability measure. The fact that there are some probability measures that run into problem is a sign that I couldn't take any generic one. Okay, but it's easy to fix it in this context. That is not necessarily the problem, but it's related to the problem because it's related to the fact that I don't know which is the choice that I should make. Okay. All right. The trick that I will use, or at least is the rationale more than the trick, is that the fact that the FPV equation admits steady state solutions. In other words, the phi distribution after a sufficient time reaches a form which changes with time, but only by an overall factor. And so the functional dependence on phi remains constant and has a universal asymptotic behavior at large times. So although we cannot compute the overlap between these steady states and the reheating surface, because we don't know how to calculate the reheating surface, the property of remaining identical in time is indicative of the fact that they carry some physical information. So in this sense, I have conjectured that critical points are attractors during inflation, and that my calculation can be taken as, I would say, supporting evidence, but certainly is not a final proof. And no final proof can be given until the measure problem is solved. There are other issues in the time scale for reaching this steady state configuration is very long, and in particular requires that the number of inflationary E-folds exceeds the de Sitter entropy, okay? So this means that my applications, first of all, they must be in the regime of eternal inflation, and it's debated whether the semi-classical approach can be trusted after this time. And then there are various issues with swampland conjectures. because the field excursions have to be super Planckian, as is the case of inflation. This is not a problem for quantum field theory, okay? Because we enter the quantum gravity regime only when energy densities are super Planckian, not when field excursions are super Planckian. And since the potential that I consider are very shallow, super Planckian field excursions are perfectly consistent with quantum field theory. However, the super Planckian excursions recently have been argued that they live in the swampland. Of course, one could introduce like a non-trivial monodromy or clockwork structures to get rid of that, but I won't try to do this. Okay, so all this to say that there are many open problems, but let me for a moment set them aside, and let's accept the hypothesis that I can give a probabilistic interpretation of the FPV equation, and let's proceed. So to solve the FPV equation, we need to specify the potential of the field phi. And this is the model independent, the model dependent part of the construction. However, one can use a useful parameterization that we have introduced that describes at least a class of theories, which we call the EFT potentials, because so the EFT potential has a logic of effective field theory and is made of two terms. The first is a constant term that describes the bulk of the energy density, and therefore this is the primary driver of inflation. And the second term is a modulation of the energy density due to the field phi, which we call the apeiron. This is described by two parameters. One is the field, the typical field excursion, which I will call it F, the language of the axion, and an overall coupling, which I will call it G epsilon. So the potential is protected by a shift symmetry of phi, broken only explicitly by the small parameter G of epsilon. So you can think of the apeiron as a pseudo-Goldstone boson of a symmetry explicitly broken by this G epsilon, or a modulus of a supersymmetric hidden sector. But for me, microscopic details of the theory really don't matter for my discussion. I will just use this as an effective theory. And the function, this function omega is a generic function of order 1, so it's power expandable around a generic point, which with a coordinate shift, I can always call it 0, I call it the origin. So because of the linearity of the FPV equation, it is useful to expand its solution in stationary states, very much what you do with the Schrödinger equation. Okay, so lambdas are the eigenvalues that describe the time dependence. So lambda are the analogs of the energy levels in the case of Schrödinger, and small p are the time independent eigenmodes that satisfy this equation. It's really the logic is the same when you solve Schrödinger equation. And here there are two parameters that I've introduced. A parameter alpha measures the inverse of the apeiron coupling, and beta is the field range, measure the field range in Planckian units. They've been chosen in such a way that alpha measures the strength of the quantum term relative to the classical term, and beta measures the strength of the volume term relative to the classical term. So the parameter alpha and beta are sufficient to parameterize the full stochastic dynamics within this class of EFT potentials. So the behavior of the FPV solution can be classified in the space of alpha and beta. Now, I won't go into the details, but let me just simplify tell you what are the three most important regions. In the region C, the classical region, the distribution mainly follows the classical equation of motion, and the field prefers to evolve towards minima of the potential as usual. However, in the QV region, there is an interplay of different effects. So the field phi naturally evolves along the classical equation of motion. However, because of quantum effects, there is a tail of the distribution where the field is at a higher point of the potential. And these configurations have a faster expansion rate, and therefore the volume of the corresponding patch grows much more than the surrounding space. So as a result, when steady state is reached, the phi distribution is peaked around a field value which is closer to the top of the potential. And the more quantum the dynamics is, the higher it climbs. Okay, or in other words, the larger alpha is. So the width of the distribution in this case has a universal value of Planckian size, which is independent of the interaction strength. Finally, we enter the Q square V regime, where quantum diffusion becomes so strong that the peak of the distribution is entirely pushed towards the top of the potential, and the width of the distribution grows the more quantum the system is. And indeed, these three behaviors can be shown analytically if you take the case of an exactly linear potential, which is just an approximation, but then you can do you can solve it analytically very well. Okay, so you can think of this asymptotic distribution as a sort of a thermal equilibrium that is reached after a relaxation time. Actually, this analogy is rather pertinent, so let me expand on it. Thermal equilibrium doesn't mean that the system is static. On the contrary, atoms move all the time, and then the microscopic configurations change. However, some macroscopic properties remain static, at least in a statistical sense. And these are the thermodynamic quantities, such as temperature, pressure, and so on. And the same happens for the multiverse. So each configuration of the field phi keeps on evolving as a result of the classical force and the quantum diffusion. In other words, each Langevin trajectory keeps on going with its random walk, just like a single atom. And indeed, the Hubble rate plays exactly the role of a temperature if you interpret it as a Gibbons-Hawking temperature in de Sitter space. However, when we look at the multiverse as a whole, we see that the macroscopic field distribution reaches an equilibrium state with some global quantities that remain invariant, exactly like the thermodynamical properties, right? The existence of this steady state configuration, or if you wish, equilibrium states, is the reason why we dare to make probabilistic interpretations. Okay, so this gives you now the tools. Now let me attack some three physical problems. So the first one is the NEAR-CRITICALITY of the Higgs coupling. I'm sure that you know that one of the surprises of the measurement of the Higgs mass was to find that the standard model, if extrapolated to a large field domain, shows a non-trivial vacuum structure with our usual electroweak vacuum being metastable just at the edge of a critical behavior. So now let's suppose that the standard model coupling constants are not constant, but depend on a scalar field subject to large fluctuations during inflation. So this scalar field is what I was calling apeiron before. And the scalar potential of the theory is given by two terms. So the first term is a shallow apeiron potential, where M is the energy cutoff of my effective theory, and G star is a generic coupling of order 1. And the second term is the Higgs potential, where the Higgs quartic lambda is a function of phi. So for simplicity, I take the Higgs value fixed to its physical value of 200 46 GeV. So I always have the freedom to choose the quartic coupling renormalized at the cutoff scale as proportional to phi. And then renormalization group effects will make the dependence more complicated since all the standard model coupling constants may generically be functions of phi as well. But let's look at the effective phi potential. So as long as phi is sufficiently small, the Higgs potential is minimized at the electroweak vacuum. And the phi potential grows with phi. This is what I call it here, IR phase. However, once you cross a critical value, the quartic starts becoming negative at large field. And the Higgs potential develops a second minimum near the UV cutoff, and the Higgs undergoes a phase transition. And this gives a back reaction to the phi potential with an additional contribution which changes its first derivative. And this is what I call UV phase. There is a small field region where two phases can coexist. If the IR supercooled branch terminates when the IR phase becomes unstable under Hawking-Moss instantons. And if you solve the FPV equation by taking the apparent potential in the Q square V regime, the very quantum regime, you find that the steady state solution has a sharp peak localized at the point where the IR phase collapses. This can be intuitively understood from the behavior of the simple linear potential that I showed you before, right? That you climb up to the maximum point. The conclusion is that the critical point where coexistence between IR and UV phases terminates becomes an attractor for the field phi during inflation. And this is what SOL is all about, right? The distribution becomes dynamically localized at a critical point. At the end of inflation, there is a strong probabilistic preference for patches of the universe where the Higgs self-coupling is near its critical value. And so then the actual calculation shows that there is a region of values of the cutoff energy M and the Hubble rate H, shown in this figure, where the prediction from SOL is consistent with observations. And the SOL, of course, the SOL prediction refers to the end of inflation. So the question is, what happens if, what happens to the SOL prediction during the thermal phase of the universe? After inflation, the apeiron finds itself at a point which is not the minimum of the potential. Therefore, after reheating, the apeiron will start sliding down the potential, slow rolling in search of a minimum. And the most dangerous consequences of this late time motion is that the vacuum energy becomes now time dependent, and astronomical observation gave a constraint on the parameters of the EFT potential, and this is what forced us to be in the Q square V regime, and therefore to be in eternal inflation, which is perfectly obvious. Now, the next example that I want to present is Higgs naturalness, or the puzzle of Higgs naturalness that we talked about yesterday. Can also be rephrased as a problem of criticality. Out of all possible values of the Higgs mass, why has nature chosen to be so miraculously close to the critical point that separates broken and unbroken phases? And so let me now consider the case similar to what I was doing before, but now the case in which the apeiron scans the Higgs mass. The scalar potential is given by the usual apeiron EFT potential, and by the Higgs potential with a phi dependent Higgs bilinear. And notice that by dimensional analysis, this potential is consistent with naturalness, because when you close Higgs loops, effectively you replace every H square term with an M square term, where M is is a UV cutoff of the theory. So loops do not generate any new structure in powers of phi. Now, the phase transition between broken and unbroken electroweak is not very useful for SOL because it is second order. This means that it induces a discontinuity only in the second derivative of the phi potential, which is not sufficient to localize the distribution at the critical point. However, we can use the non-trivial vacuum structure of the standard model Higgs theory. So let's suppose that the Higgs quartic coupling is negative at the cutoff scale, just like in the case of the standard model. So the effective apparent potential on the Higgs background exists in three phases. One is the electroweak phase, which is the usual, which is the one in which the Higgs value is 0, the unbroken phase. Then there is the IR phase, which is the familiar one in which the Higgs has a low field valve. And then there is a third phase, which is what I call a UV phase, where the field resides at high field value. So the IR phase has a termination point at the value of phi, where the Higgs bilinear mass becomes larger than the scale where the Higgs quartic crosses 0. Beyond that point, the Higgs potential is monotonically decreasing with no local minimum, but with an unbounded direction up to the cutoff, and then I don't know what happens. When you solve the FPV equation, you find, unsurprisingly, now you've seen examples, that the distribution is peaked on the IR phase at the edge of collapse. And this gives the sole prediction that the Higgs valve is approximately equal to the instability scale, in the scale at which the Higgs quartic vanishes. And this result is, I think, remarkable because SOL can create a natural hierarchy between the Higgs valve and the cutoff, the UV cutoff M, as a result, essentially, of dimensional transmutation. And this gives an exponentially small ratio for V over M. Of course, in practice, this prediction is not very useful, very successful, let's say, because in the standard model, the instability scale is in the range of 10 to the 10, 10 to the 12 GeV. So phenomenologically, one can reconcile this prediction with experiment by adding new matter at the TV that lowers the instability scale. So for instance, one could add new vector-like fermions that with certain arrangement can fix the problem. Okay. Now, in summary, SOL naturally generates a hierarchy between the Higgs valve and the cutoff. However, you have to modify the standard model somehow. Now, looking at the bright side, you could interpret this as a phenomenological prediction, right? Because there must exist new matter that modifies the Higgs quartic beta function such that the theory is near critical with respect to variation of the Higgs bilinear. And in other words, the theory is at the verge of collapse with respect to variations of the Higgs bilinear. So let me come now to the third and last example of SOL applications, and this is a cosmological constant. Now, here the story is significantly different from the previous two examples. So imagine that the microscopic theory is some extension of the standard model, and some of its parameters are functions of this scalar field. As the apeiron varies in its field range and scans the parameter, the microscopic theory can reside in different phases, like what was happening for the Higgs. Now, on one vacuum, which I will call it H for hidden, the theory preserves some of its fundamental symmetry. So it's supersymmetric and R-symmetric. As a result, the vacuum energy vanishes because all auxiliary fields vanish on the vacuum because of supersymmetry, and the superpotential vanishes because of the R-symmetry. obviously, this doesn't look like our universe. So we live instead on a different vacuum of the theory where supersymmetry is broken. And I will call this vacuum phase V because of the visible phase. Next, assume that there is an inflation. And this uplifts the theory to de Sitter. But after inflation, then relaxes to a supersymmetric vacuum. So in summary, the apparent potential of the theory looks like this. In phase H, the apparent potential is flat with a vacuum energy given by the inflationary contribution. While in the visible phase, the apparent has a certain model-dependent functional form, which scans the cosmological constant up to the cutoff value. Moreover, transitions from phase H to phase V can happen beyond a field value, which I call it phi t, the transition point. Instead, phase V is stable. There is necessarily one field point, which I will call it phi c, where the two phases are degenerate. But notice that there's nothing special with this point phi c, okay, for either phases. Nothing happens in that point. The gradient of the potential is not zero. There's no transition, no special symmetry at that point. If some appropriate boundary conditions are chosen, and in this case, the boundary conditions are important, the asymptotic solution of the FPV equation shows a sharp peak on the phase V at the critical point, where the two phases are degenerate. And the relative probability of landing on the visible and hidden phase depends on the parameter choice, but there is a large parameter range where the probability for the universe to be in the visible phase at the critical point is absolutely overwhelming. Okay? So after inflation, the energy density is reduced, and the visible universe will have an approximately vanishing cosmological constant. I think the result is remarkable because an observer who lives in phase V will not see anything special in the zero value of the vacuum energy. It's not a point of enhanced symmetry. It's not a point in which the theory undergoes any critical behavior. So the secret of the result lies in the macroscopic behavior of the system. So a single Langevin trajectory, or in other words, a single universe, doesn't see anything special at the point phi c. Just like a single atom in a gas doesn't see anything special in one particular value of the energy, doesn't know about temperature. And yet, just like when you put in thermal contact two boxes of gas and the energies of the atoms arrange themselves statistically to give a single value for the temperature of the full system. So the field trajectories arrange themselves to reach a steady state configuration in which the expansion rate is roughly the same in both phases. And since the expansion rate is proportional to the energy density in the visible phase tries to align with the energy density in the hidden supersymmetric phase, even if the visible theory doesn't know anything about supersymmetry. And this is the underlying mechanism that explains the cosmological constant in a statistical sense within the universe. Notice also the different new way of using supersymmetry. We are used to think of supersymmetry as an extension of the standard model that modifies the Higgs properties. In my context, supersymmetry is a completely hidden feature of the theory to any observer like us who live in the visible phase. But supersymmetry becomes visible only if we could move away from our vacuum. And yet it is what determines the physical parameters measured in our vacuum. And now, okay, there are some details. When you solve it, you find a certain constraint on the reheating temperature. But let me just say that maybe the most interesting aspect is that the theory then gives a prediction for a modification of the dark energy equation of state as a result of that. And the parameter W, which measures the ratio between dark energy pressure and energy density, is expected to differ from the usual value of -1, which corresponds to a constant, cosmological constant. And future measurement in observational cosmologies will reach precision better than 1% and can really test these predictions. So let me get to conclude, and let me conclude with one remark, right? Soul seems a very speculative subject. We are talking about the multiverse and the dynamics occurring well beyond our event horizon. However, in spite of its speculative nature, we can make testable predictions out of soul. So the soul's smoking gun is phase coexistence. This is the essence of the mechanism. And in the first two examples that I was showing, the universe is at the verge of collapse, at the verge of a phase transition, with respect to some parameter variations. So the case of the Higgs self-coupling is really prototypical of this. A small change of the parameters make the standard model collapse into a different phase. Of course, the experimental test does not lie in making the universe collapse, but in measuring standard model parameters so precisely, and then to extrapolate theoretically the effect of varying them. So for Higgs naturalness, new matter must be added to make the standard model near critical with respect to the Higgs bilinear, and that is the prediction, which actually could even be tested at the LHC if you like. The example of the cosmological constant is, I think, more complex. It is more complex to disentangle experimentally, since the hidden phase cannot be reached by parameter distortions. Nevertheless, there is an observational test, and the observational test lies in a measurable modification of the dark energy equation of state. So I believe that Soul offers an example of an approach radically different from the usual paradigm based on symmetry. And the central point has a simple physical basis that critical points can become dynamical attractors during inflation and determine low energy parameters. So criticality in the multiverse can lead to parameter predictions that do not correspond to any enhanced symmetries, and that will certainly defy ordinary EFT logic. The analogy that I've been using is with atoms in a gas in thermal equilibrium. So if I take one single atom and trying to infer its energy from fundamental principles, I just simply don't go very far. Okay? Any energy is as good as any other for a single atom. But if I interpret that atom as a part of an ensemble using statistical equilibrium distributions, then I can tell you which energy is the most probable, and this is related to temperature. So similarly, trying to derive some of the standard model parameters from fundamental principles may not lead us anywhere. If I look at a single universe, any value of those parameters is as good as any other. But if I interpret the universe as part of a multiverse using statistical steady state distributions, I can infer that critical points may be probabilistically preferred. And this is the important new point. Some people erroneously associate the multiverse only with anthropic arguments. I'm saying here that there is much more than that, and I'm proposing to look at the multiverse as a quantum statistical system. Well, I am in a sense, right? I am, in a sense, I'm using an analog. I mean, after all, the Fokker-Planck equation is indeed, it was started to describe, fusion system, so to describe a thermal system. I'm just using exactly the same language, but transferring it in the language of quantum statistics and applying it to the universe rather than to single atoms. But there is an analogy. But of course, when I say temperature, you shouldn't think about temperature, but you should think of a parameter. So I'm using certain parameters of the Lagrangian as the thermodynamical quantity. So there is a strict analogy, but not physically, is not the same thing. Yes, that's exactly what I'm saying. Okay, so it's not the temperature, but those parameters will have then we will trace the statistical system. Did I answer? Okay, so let me just conclude. This is the last slide, and I think I've shown that SOL can address some of the classical open questions in particle physics. I discussed the parameters of the Higgs potential, the cosmological constant, but I think SOL is a flexible tool and could offer new handles to attack other problems in cosmology and in particle physics. Higgs naturalness remains a great mystery, and we cannot say that we have understood the electroweak breaking until we get to the bottom of this question. And I think that one of the lessons that we may have learned from the LHC is that we must expand our horizons in dealing with naturalness, and I hope that SOL will help us expanding our horizons. Thank you.
Provoking talk. So questions, Rick?
While it's really amazing how these parameters are driven to their critical values, I had like a different question. So once you have, like, let's say many universes, or let's say, so anthropic selection is unavoidable, right? So like for the last two cases, the Higgs mass and the cosmological constant, I mean, do you need a selection? So if you have many universes where, and only some can allow life, I mean, do you need the problem many people might have with anthropic selection is the first part where you need to have many universes with parameters varying. But since you have that already, you will automatically, or is it that you are not convinced by the anthropic argument for the Higgs mass? Or
I think that once you are in the multiverse, certainly, different parameters will have different explanations, and it's quite likely that some of them may have an anthropic explanations, and it is possible. Here I'm trying to explore something more than that. Okay. In particular, I've shown some examples which have possibly an anthropic explanations also. In that case, I would replace it by a dynamical one. I certainly prefer to have a dynamical explanation, but I'm not necessarily discarding other possibilities, but they are not compatible. Okay, so either you choose anthropic or you choose a dynamical solution. You don't.
So that's what I was trying. So like in your case, let's say if the phi varies. I mean, even if it's not local, like you will always select the parts of the universe where the phi is compatible with the small cosmological constant, right? So I mean, it's unavoidable that you will like if you have many possibilities, you will only have those where life is allowed. I mean,
I'm going beyond that. I'm just saying that you don't even need to select out of all the universes where those consist. I mean, then it becomes, in a sense, the anthropic selection becomes a consequence of dynamics, because it turns out that the dynamics will tell you how critical, and then in particular cases where the critical value is also anthropically preferred, then you have to do it. Okay, I think it, you know, it's clearly a exploratory exercise, so it is a first example of showing, and I can imagine that it can be applied to other problems where you don't have an anthropic explanation. And then, for instance, the Higgs instability there, you know, I'm not aware of one. I mean, you can always try to think, but so that in particular shows so I'm not worried that in some particular examples you could also have had a different explanation.
I had another
very. No, it is more interesting. I find it more appealing, right? In this full dynamics, you see that the critical points are attractor, and that gives you an explanation. As I was showing in the beginning, right? There are many selecting criteria. For instance, take the axion. They say, oh, but does the axion do that? Well, in case of the axion, you know already that there is a symmetry criterion that gives you the selection. And so it may work also inside, but in that case, inside the multiverse, but in that case, it's really symmetry that determines. I mean, my picture is that if we really had a multiverse, it doesn't mean that all explanations now are given in one way. Certainly, symmetry will certainly play a role, and maybe anthropic selection in some cases, and maybe the criticality in another one. I mean, we are really going to an unexplored land, which will not be as simple as one criterion solves everything. But as always, in a new territory, you're going to find many savages inhabiting that region.
I had another very quick question. So in the experimental consequences, like is there a possibility you can see the phi in the Higgs naturalness and the self-coupling case? Because the phi will probably mix with the Higgs, and then maybe it can be like a Higgs portal. Or I mean, I don't know if it's a big mixing or not. And
it's very small, because I mean now it depends on your scale that you put. But as you well, I haven't really shown you, but essentially when you solve this equation, you need to be in eternal inflation, and so you need that the field range is enormous. Okay, much bigger than in Planck, and that is what then describes the effective scale, like the axiom scale of the coupling. So that the field phi is really decoupled. So there's no hope that you can see it in a collider experiment. But what you could see is instead is the other states that you have to introduce in order to modify the beta function. Since those modify the beta function, they have to be sizably coupled to the Higgs. Those are the states, not the phi. Doesn't matter.
Hello. So the problem with anthropics, for example, the wickless universes or other have clearly shown like you can't have arbitrary measures to get the argument of life to get whatever you want to explain. I mean, in a sense, I mean, this is the ugly truth about anthropics. Great that you can use multiverse and move away from the ugliness of measure dependence in order to make a concrete prediction. But wouldn't you think like now connecting the Higgs wave with the criticality, I mean, you have made the problem of naturalness a lot more problematic in the sense that in the standard model, you can you can argue, okay, Higgs sector doesn't talk about whatever new physics comes in to give neutrino masses. Gravity, self-corrects itself at high energy. And so you could have somewhat said like, okay, naturalness, maybe it's not that big of a deal. But now in your case, you can't live without having something extra, new physics and stuff like that coming
in. Yes, I mean, in a sense, I agree. I started to go away from the symmetry principle, and so saying, oh, I will not have new physics at the electroweak scale. I make all this long path, and I get back to the case in which I have that. I have new states at the electroweak scale. It's just, but I take it as a coincidence. Notice that these states also are vector-like states that do not affect the quadratic divergences. So in themselves, they do not add to the naturalness problem. But I agree with you that it's kind of peculiar that you find yet again the case that there is new physics at the electroweak scale, even if in a sense I try to do everything to avoid it, right? And this goes back to what we were discussing yesterday, that it's the exploration then of new scales, of new physics with new colliders does not necessarily need a naturalness for explaining. And this, I find it, curious and supporting that argument. I follow the logic in which I don't want to have new physics at the weak scale, and I go through the multiverse and so on, and then I find a new scale at the TV scale, new physics at the TV scale. I don't have deep answers.
This may be a bit basic, but there have been experimental attempts to constrain the variation of some of the fundamental constants over time, like the fine structure constant. And then also theoretically, I think there were attempts to think of the cosmological constant as being stochastically fluctuating in time. So does your approach say anything about the variation in time in a given universe of the parameters?
Yes, it does. And actually, that is that I use it as constraints. Because as you see, I have a time variation of parameters in general. Because see, the scalar field at the end of inflation will find itself in a place which is not a minimum. This is because of this dynamics. And then after inflation ends, this dynamics will not support that field, and so this field will start rolling down. And since this field is what measures physical parameter will have a time dependence. And indeed, this gives a constraint on the models that I was constructing. And the constraint, as you can imagine, is that the potential of this field has to be very shallow, because otherwise the time dependence is too strong. And as you know, the shallower the potential, the more the quantum dynamics becomes important, because the classical motion now is very slow, and so you are much more affected by quantum fluctuations. And indeed, that is the ultimate reason why all these models have to be in the regime of Q squared V, because that is the regime in which the potential is very, very, very shallow. At the end, usually, at least in these cases, the stronger constraints comes from the time variation of the vacuum energy. It's much more important than the time variations of the masses of the particles, of G Fermi, of G Newton, that they all have a constraint. The strongest constraint comes from variation of the vacuum energy. And that is indeed the reason why, in the case of the of the cosmological constant examples in which I cannot change it completely. I cannot tune it away completely, this effect. This effect is the experimental test, because essentially I'm using the constraint that the cosmological constant cannot change it too much, but I also find that there is a remaining time variation which is there, and that is what modifies the equation of state of the dark energy. So absolutely it is there, and it is a model dependent question in some cases to avoid that too much of a time variation. But it is intrinsic of the model to have a time variations of the parameters. And case by case, the parameters are different.
So first I have a very general question. So this going beyond symmetry paradigm, so that in condensed matter system, you know, that is a known thing. Criticality is a very known thing in condensed matter system. So and that first is not that we're not taking symmetries any more seriously, no. So so it's just an application of this idea of multiverse as a statistical system to a more high energy context. So so idea wise, is there something really new from what is already known in condensed matter system?
I think that you are absolutely correct. Much of the physics is borrowed from condensed matter or statistical mechanics. And indeed, you know, even the terminology that I'm using, the Fokker-Planck equations and so on. This is, you know, we are sort of moving in this unexplored territory, and I need some handles, and the handles are using physics that we know, and therefore using what we know in statistical mechanics and in condensed matter. And I wouldn't be surprised that some of the concept there then can be translated in this language and re-understood. Is there more? Well, I mean, think back at the time of the Higgs, right? I mean, the Higgs mechanism was discovered by Anderson in condensed matter. Okay? This is a fact. And then you say, okay, but then what the particle physicists did? Well, translating it. And this is Nambu who understood that that language there could have been useful also in high energy physics. So translating some language discovered in one field into another field is not necessarily a trivial exercise. Oh, it was already done. No, you may find new things, because here the physics is completely different than condensed matter. I mean, a condensed matter physicist cannot construct a universe in his or her labs, right? But I think that this connection is indeed, I find it very interesting. This is why I really wanted to phrase the multiverse as a quantum statistical system. And just saying that as a sentence opens your mind towards using different techniques for the multiverse. I think most of the people, when you say multiverse, they think, oh, it's anthropic and that's it, okay? And I'm just saying that there's a lot more than that. And using this terminology is a way of suggesting to people that they should use that language. And I think there's a lot more to be discovered, especially by people who may even be more familiar.
Also, it is just a question. So is it true that all quantum statistical systems will have this phenomenon of criticality? You may have systems where this is not realized, right? So in some sense, we are, I mean, it's not very clear that we are, I mean, it's an interesting statement by itself, but I'm still is an hypothesis where it's saying that, okay, this one quantum statistical, the multiverse is one very special kind of quantum statistical system.
Yes, but I mean, it's, this is exactly why I use this terminology, self-organized localization, right? It's hinting towards self-organized criticality. And again, the logic is identical self-organized criticality, but not all the systems in nature satisfy self-organized criticality. Okay? So you cannot say that, well, everything is. Some systems do, some systems don't. And indeed, that's what you find in the multiverse. It's not that you say, well, for any parameter, then you should be critical. No, it depends. Even in some of these examples, I had to work hard to find then the right setting in which the critical point becomes attractive. So it's not automatic that in the multiverse necessarily all critical points are attractive. It depends on your specific dynamics, very much as happens in.
Yeah. So isn't it like just the deferring the question one more step by one more step, the question of hierarchy, naturalness, and cosmological constant and Higgs? We're just saying that why even self-organized criticality is realized in multiverse.
I'm not so sure that I agree, in the sense that we know that self-organized criticality works, and we understand the dynamics of it. Yes, I've used that language, but in a sense here I'm not deferring the question, because I'm just giving you the full dynamical model, and I'm showing that the critical point is attractive. What more do you want in terms of rationale? And
I would say, you see, for example, there are many different kind of condensed matter systems. Some systems have some interesting behavior, some other systems, some other kind of interesting behavior. Now, why multiverse as a system has a particular behavior? Now that, is in that sense, is just one material, right? In the zoo of, okay.
Okay. No, I see your point. Maybe I'm less ambitious. I think I'll be happy enough to see that this is realized and why the universe chosen to be like that. Yes, I defer that question, but
yeah, sorry. One very quick. Sorry. So now, since we are thinking of multiverse as a statistical system, if I apply laws of thermodynamics, for example, second law of thermodynamics, am I going to get more interesting information from this kind of system?
Yes, I think that you could. I am here. I've worked on equilibrium systems. See, I have I've done all these dynamics. Yeah, I saw the dynamics, but then all the physics comes only in the equilibrium system.
It's only finally, if I understood correctly, because you also mentioned that this, in the context of time foliations, that it doesn't matter because finally.
I think it is interesting. I mean, because I saw the easiest part of the problem, because the equilibrium dynamics is simpler than non-equilibrium dynamics. And so I have solved only that, and so issues about the change of the entropy and so on are not so relevant for my specific question. But they will be very relevant for how you reach that system. And indeed, as I showed you, I'm finding that I violate the entropy bound and so on. And those statements all refer to the way you reach equilibrium. And many of the problems about the probabilistic interpretation that was mentioned in the beginning do not refer in the final state, but really they refer to the way you reach equilibrium. Because the way you reach equilibrium requires a huge amount of time. You say, well, the universe has enough time. Well, it does, but then you run into all these problems about swampland conjectures, entropy bounds, and so on, exactly because you need this very long dynamic. So if I could change that part, it would be quite interesting. Maybe not necessarily for the physical consequences, but it would be interesting for the model construction because it would give me more freedom. And I haven't played much with that. At the moment, I'm thinking more in the direction of what can I do with a measure problem. But that, in principle, could be a very interesting research direction. But I don't know where it's going to go.
Yeah, sure. So does the multiverse being in the steady state mean that all the universes are near the critical point? I mean, are all universes supposed to have similar parameters?
So, probabilistically, yes. probabilistically. Okay, so you have you know, as I was giving the example of the atoms, right? When you are in thermal equilibrium, it doesn't mean that all the atoms are still, right? All the atoms are still moving, but you have some properties that in which you can trace the whole system. And same here, you know, universes will continue to create, expand, and so on. And each of them will have their own values of the parameters. But I'm saying that if once you reach that condition, there is some global properties that tell you, I mean, each individual universe doesn't know anything special about the parameter, but when you look at them, you see that there is a probabilistic preference towards a value. Probabilistically, okay? You can always find a universe that has a one parameter that's way off. It's like, you know, you have a system that has a certain temperature, but you can still measure that one atom has an energy which is really, really different than the value of the temperature. So it's something like that.
Okay, so probabilistically, our universe is not unique in the multiverse, right? Or
probabilistically are not unique. What do you mean exactly? Sorry.
Okay, maybe I'm not making sense, but yeah, I understand the point.
We can talk then during the break.
Thanks.
I didn't understand exactly your question.
Hi.
Please go ahead.
So hi, Gian. This Fokker-Planck type of equation you wrote, that is not a standard equation that occurs in ordinary statistical mechanics because of this PHV term. Can you explain that term a little bit more? That's one question. And secondly, your Langemann equation will not lead to this equation, I think, because of this PHV term.
I mean, you have to also modify the legend.
Okay.
In that case. So the idea is the following, right? You are, of course, absolutely correct. That so I have this statistical system, but then there is another effect that I need, another physical effect, and I need to put this input, and which is the expansion of the universe. Okay, so which tells me, since I'm counting volumes, because for probability I'm counting volumes, if I don't add that term, I'm missing some of the most important thing, which is the fact that the space expands. You say, well, okay, but then it's a global expansion. No, because the expansion rate now is field dependent, and that is a trick, right? Because that's why I need to count. Otherwise, it would be just an overall factor that I can eliminate. But it's not, because this factor of the expansion depends on the universe in the sense. So it depends on the position of the field phi. If the field phi is at a higher point of the potential, there the vacuum energy is bigger. There is more expansion. Therefore, I gain more in terms of volume. And so that extra term is modifying the usual statistics to take into account also the fact that the space expands in a way that's not uniform and favors. And this is actually why do I go up in the field phi? Exactly because although it's energetically disfavored to go up the potential, I have a favor in terms of the measure of the volume. And this, in some cases, can compensate or overcompensate the other effect. Of course, by doing that, as I said, I'm losing the sense of probability density, because now it's not anymore conserved. But this is really the consequence of the fact that my space expands, and therefore I cannot take observation. Okay.
So, like, so you are modeling basically the multiverse in this context of a gas in statistical equilibrium. Now, all systems attain statistical equilibrium via collisions, interactions amongst the constituents. So, if two such universes having completely different physical constants come in causal contact with each other, so how will an observer inside one of them interpret this event?
Right. So, indeed, one should not push the analogy too far. There's not an interaction between the different atoms. So, in the case in this case, it is the phi dynamics that what makes in a sense, universes to talk to each other. They don't talk to each other, okay, but they keep track of the information depending on the dynamics of the field phi. And that what is the link between the different universes. So you should not think that thermal equilibrium is reached because universes collide and exchange information, but it is because of an overall evolution of the scalar fields that does the job and communicates information in a sense between the universe.
Okay. Higgs criticality is very important for the multiverse motivation, right? Suppose if you make it stable all the way, because by adding some extra particles or something, then what would be the motivation for multiverse? Cosmological constant?
Yeah, I mean, I think in general, for me, I gave you 3 problems to show you that there is an array of possibilities that could be studied. It's yes, just because also in the past I've studied this issue of the Higgs criticality. I certainly, that was one step in which I started, but I don't view it as a motivation of it. I mean, the multiverse, as I was arguing yesterday, I don't see it as an hypothesis, but rather as a consequences of other hypotheses, and the other hypotheses are related to inflation and so on. So once you have it, I think it is interesting to study it, and then I connect it to some physical questions. But I don't think that I would use Higgs criticality as the Corti criticality as a motivation of this. So suppose that tomorrow they find new particles and they find that the standard model is stable all the way. Would I lose interest in this? No, because I think, yes, okay, there would be one example that I would not present in a talk, but still, I think that the whole framework, conceptual framework that's behind it goes way beyond the specific example.
Any other question? Okay, Shilpa.
So I have a very basic question that in these quantum phase transitions, so how these phase transitions occur, and like in the first order phase transition, some kind of barrier is needed between the 2 phases. So like some kind of cubic term can generate this barrier, but here, like what is the term, or like how the barrier is generated for the transition? Okay.
So first of all, as I mentioned in the beginning, remember that these are not thermal phase transitions, okay? So for instance, at a certain point, I said that the electroweak phase transition is second order. I mean, the usual electroweak phase transition at high temperature is not second order, right? The point is that here I'm looking at a quantum phase transition. So when I was saying second order is not because of temperature, but because of something else. And that something else for me is a variation of parameters. So if you just take the standard model in isolation, that is not a physical phase transition, because it just it's something that you can do in the blackboard or changing the parameters. I'm making it physical because now I'm saying that those parameters depend on a field. And so as the field moves, it creates a phase transition. So the agent of the phase transition is this field phi. And what happens is that in the universe, as this field phi moves, and it moves stochastically, so it's like some random motion, in some points, at a certain point, it triggers the phase transition in the volume of space where it goes in that region. Okay, so there's no temperature, but in a sense, if you wish, the role of the temperature is played by this scalar field. It's a purely quantum.
Okay, thanks.
Thank you.
No other questions? Okay, so every good thing must come to an end. Thank you again, Gian, for an excellent talk.
Questions.